Okay, cool. So we are MRover, or the Michigan Mars Rover team, one of the many project teams here on campus. This presentation will go through building astronaut-assisting rovers for Mars exploration. So we'll start by introducing ourselves. My name is David Baek. I'm an incoming master's student. I just graduated, and I graduated with a major in mechanical engineering. I'm getting my master's in space engineering. I am the outgoing president of the team, and I was the former mobility lead as well.
Hi, my name is Rachel Lee. I am a rising senior this year. I'm a mechanical engineering major, and then I am our current incoming president, and then formerly I've been our mobility lead as well as treasurer.
So what is the Michigan Mars Rover team? So we are a multidisciplinary robotics team, and every year our goal is to build a Mars rover to compete primarily at the University Rover Challenge, which is an international competition in Utah. Our team was started way back in 2000, but it looked a lot different back then. And I think we've only actually been building rovers for less than 10 years. And currently we have about 80 undergraduate members. We saw kind of a boom in membership maybe 3-4 years ago. And those members are split up into 5 technical branches and 14 subsystems, or subteams as we call them. And on the right, you can see us in Utah at the competition, the last one being actually 2 years ago, which is pretty disappointing, but we will make do.
Okay, so I guess a bit of what we do. So first up, we compete in 2 different international competitions. Like David said, the main one is University Rover Challenge, and then the second is one hosted in Canada. And then our main goals are really, to develop skills for all the students on our team and apply them to space exploration directly. So we're giving people hands-on experience with designing, building, testing a rover. And then while we're at it, we really try to get people interested in space exploration, and also, growing diversity in the College of Engineering and the Wilson Center. And then, again, kind of giving all our team members experience in that, as well as real world project life cycles and deadlines. And then you can see in the picture to our right, those are again pictures from our last competition in 2 years ago in Utah. So this is the space where we work. I think a lot of students will be familiar with it, but it's the Wilson Student Team Project Center. It's where most of the project teams are housed at the university. So the left image is our own workspace. It looks very clean in this picture, and it actually shows our rover from 2018 atop the table. And then the image on the right is just the machine shop that all the teams have access to. So we've got manual and CNC mills and lathes all available, as well as other machine shop tools. And so that's where we get most of our work done, especially mechanically, where we manufacture our rover almost entirely in-house, and this is where it happens.
So about this competition, the main one that we try to succeed at is the University Rover Challenge, or URC. It's hosted by the Mars Society. It's held at the Mars Desert Research Station, which is near Hanksville, Utah. It's very far from civilization. It probably is used as a Mars Desert Research Station because it's one of the places on Earth that most resembles Mars. The terrain is similar, the dirt texture is similar, and that's where we get to test out our rovers. About 80, sometimes 90, and sometimes more teams apply to get into this competition every year, and only 36 actually get invited to compete, just because it can't accommodate everyone. This year and last year it was canceled due to COVID, but we did build a new rover each of those years, and we have been doing testing to measure our progress. So just go ahead. Sorry.
The competition is split into a couple of different missions, or tasks as we call them. So the first is going to be extreme retrieval and delivery, where we are really testing our ability to go over like difficult terrain and navigating. So in the left, you can see us moving a hammer between very specifically designated workspaces. And in the right, we have to travel through like a ravine to deliver a water bottle to an astronaut. And so this mission also includes like a rock garden and like climbing of slopes. So that really tests our mobility and arm systems, which we'll get into.
Yeah, so we'll go through kind of each system with each that's relevant to each event. So for ERD, the robot arm is very important. Our robot arm uses 6 degrees of freedom, the majority of which use a custom cyclodal transmission that we design and manufacture in-house. And we use it to be able to pick up a 5 kilogram payload, which is the requirement from the competition. We also use a lead screw hand gripper, and that's what we use in order to pick up things on the ERD field, as well as control other things for other missions. So as you can see, a picture on the left are rovers typing, and there's some pictures of the CAD on the right there.
So next we have the chassis, which of course is the main body of the rover. This year we switched to a welded square tube frame, and you can see the battery mounts inside the chassis, so making it really compact and easy to move around. We have a truss design that also is used to support the electrical box, as well as the robotic arm and sample acquisition systems, which will be described later. And then the final important part of the chassis is we have a mast kind of sticking up in the middle there that supports our antenna, as well as a 2 degree of freedom gimbal camera at mid-mast, which allows us to survey the terrain without having to rotate the entire rover every time we want to see. The next system tested is our mobility system. So this year we transitioned to a rocker bogie suspension, which I'm sure people recognize from the Mars rovers that NASA has built. And then we used fully 3D printed compliant wheels that you can see in both pictures here. And so we use direct drive brushless DC wheel motors. These we actually pull off of hoverboards that you can like buy at Walmart. And we throw on our custom printed compliant wheels. And so we've been able to play a lot with like the tread design and the compliance so that we can incorporate damping and other sorts of characteristics that we want from our driving into our wheels. And we're able to maintain a ride height of 18 inches, which allows us to travel over some large obstacles like bushes, while also keeping us close to the ground to acquire samples.
So during the ERD mission, software does come into play because the rover is operated by a human operator on the team. So we design our own custom GUI, graphic user interface, and we use it to stream up to 2 camera views from the rover cameras at any time out of the multiple camera views that we have. We also use it to track different GPS waypoints that we have to drive towards, as well as, and it also gives us kind of a rundown of the rover status for safety, as well as just seeing how well the rover is doing. So the next event is equipment servicing. So not much driving here. Basically, a rover has to drive up to a lander and operate on it. And they will tell us a couple of different small tasks that the arm has to be able to accomplish on this lander. Some of them are typing on a keyboard, if we type out a certain word, or we have to pull levers, turn knobs, open a hatch, things like that. Things that, in a situation where Mars has people and rovers on it, we might have to do make it safer for the rover to do these tasks.
Right, so for the equipment servicing mission, we have a special equipment servicing attachment that you can see in the bottom left. So that allows us to get those really precise movements that we need out of the task, such as, the knobs, the handles that we need to be maneuvering. And you can see the righter of the 2 left images, it shows the 2 lasers that we have aboard the end effector. And so the point where those intersect places us at an exact distance to be typing in keyboard commands. So that's one of the features we have that allows us to have super precise movement of the arm. And so in this task, we also use the inverse kinematics algorithm that we've developed. And so essentially what inverse kinematics is instead of having an operator turn each joint of the 6 joints on our arm to achieve a certain end effector state, we have our software team generate exactly the path to get there efficiently and quickly. So that saves us a lot of time having someone be like, oh, oops, I overshot this angle and I have to overcorrect here. It has the rover do it entirely on its own, which really reduces time and allows us, again, to be super precise. And on the next slide, you'll see, so this is the board that we've developed for our own testing purposes. So we've got a lot of the features that I have mentioned before, opening drawers, moving latches. And that image on the left behind that big gray panel is actually, there's a keyboard in there. So we first have to open that hatch, and then we have to type on the keyboard, and then we'll have to reshut the whole thing. So this is just what we use for a lot of our internal testing.
So the next event is autonomous traversal, which is definitely one of the most difficult events at the competition, and most schools score the least, if at all, on this event, just because it's very hard to make a self-driving vehicle in a year. So basically, we have to on moderately difficult terrain, our rover has to traverse to a couple of different points that they tell us, and it has to completely do it on its own. So in order to do this, we actually have 3 software subteams dedicated just to autonomous driving. So a big part of it is perception. A rover has to basically know where it's going as well as see what's in its path. So it has to be able to detect AR tags that are placed on the field and sometimes drive through the middle of 2 tags, which is called a gate. And also just in terms of safety and efficiency, the rover has to be able to see obstacles in its path and avoid them. So it has to change its course to make sure it can actually drive over where it's going. And so once the rover sees the things around it, as well as locates its current position, then it goes into its navigation algorithm, which is a separate subteam, and kind of a breakdown of the decision making is on the left there. And the navigation team makes this algorithm to basically make the rover make the correct decisions on its own while it's out in the field. And all of our testing, some of our testing is done in person with the actual rover towards the end of the year. But first semester and the beginning of the second semester, the rover isn't complete, and the autonomy teams want to test out the rover. So we build our own simulator in which we put our rover through these similar situations and get to see what the rover would decide to do given certain obstacles and given certain locations of the points and AR tags that we have to approach. So we use this so that we can test basically year round.
Right. And supporting all of these missions, we have our power system. So we build our battery in-house. It's a custom 10 series 5 parallel battery that supplies 36 volts to the entire rover. And then we use a series of step-down converters on what we call our power distribution board. And that allows us to distribute power to all of our different microcontrollers, other sensors, and smaller motors aboard the rover. So you can see the battery is in the image on the left. We weld that in-house. And then the images on the right are some of our converters and the layout for some of our boards that we use on the rover. In addition, we have a communication subteam. So we have to operate the rover remotely, sometimes out of line of sight. So we use a 900 megahertz operating frequency and a 5 megahertz bandwidth. So you can see we use lip antennas on the rover and then a linear amplifier at the base station, which you can see on the image on the right. It's that big gray thing that just sticks up in the air. And then we also recently added a radio repeater. So that's the green box in that image on the left. And basically we release that in the field when we're kind of reaching the edge of our communication limit. And that allows us to increase our communication range so that we can continue, out of line of sight with obstructions in view.
So our last mission is the science mission, and it's very unique in that the rover actually has to collect a sample of soil or dirt from the ground and analyze it completely on board the rover, which was added to the rules, I think 2 or 3 years ago. Before that, the samples were analyzed by hand. But now, since they're analyzed on rover, it's a very difficult task. We have to have this testing equipment on board the rover. And basically, our goal is to see if we can detect any signs of life or extinct life in these soil samples. So the mechanical system that's involved with this is the sample acquisition system, which this year we decided to go with a 3 degree of freedom Cartesian motion system, similar to a 3D printer, where basically it decides where to go, and then it goes down and uses a scoop to pick up a sample and then return to its position in order to deposit these samples into our science boxes for analysis. On the right there, you can see it kind of in action inside the Wilson Center just to do some testing. And then on the left is a kind of a close-up of the CAD of the scoop mechanism, as well as an attachment for the microscope. And we actually use this microscope to look at rocks on the ground that we don't want to actually pick up.
Okay, so in conjunction with our sample acquisition, we have what we call sample handling. And so these are the actual onboard tests that we're running. So we collect the samples, deposit them into these boxes. We just call them science boxes. And inside we have a series of chemical tests that we run. So you can see in the image on the left, we have them labeled. So we kind of choose our own tests, what we think we can accomplish and what will give us results, because we're looking for signs of existing and extant life through these samples. So we've chosen to use amino acids, ammonia strips, and chlorophyll tests, and those have worked in the past for us, and they give us good indications of signs of life. And then we have like mechanisms inside the box that allow us to kind of exactly carry out these tests. And so you can see the image on the right is our like fully set up box ready for testing. And in addition to that, our onboard testing includes Raman spectroscopy. So we've built our own spectroscoper in-house. They're generally really expensive and difficult. And because of that, we've had a lot of struggles with our own, but this is all custom built for us. And then we use ZMAX to kind of optimize the exact type of movement of light that we're seeing. And for those who don't know, it's really just a process of non-destructive chemical testing in which you kind of just shoot a laser at a sample, and then you kind of analyze the wavelengths that are refracted back. And that kind of gives you an assessment of what type of chemicals you're seeing. And if we're seeing certain types of particles or whatever, then we can use those as indicators of sign of life.
So those are all the events. Briefly about Mars exploration. So obviously there is a big difference between what we do and what NASA does. This rover is for the desert of Utah, so the requirements are different. We work with a budget of only $50,000, which I guess is still a lot, but it's not $2.5 billion. We also have a 1-year build cycle, which proves to be a major challenge every year, and we have to work very, very quickly. We do actually work with NASA occasionally to develop science plans or systems engineering procedures. We kind of tap into their documentation that already exists for systems engineering, and we use that to kind of get a head start learning more about those systems. But being on this organization does foster a passion for space exploration, and specifically for Mars. And several people on our team have actually worked on the Mars 2020 rover that is currently on Mars at JPL. So it's definitely something that we're all very interested in. Yeah, so that basically concludes our presentation. Here's a couple of social media things. There's our Instagram, our websites, and our latest video that details all the technical aspects of our current rover. That's the title of it, so you can search that and find it on YouTube. And with that, I will take any questions. This, by the way, is probably our best photo of our current rover on the Mars yard that is behind the Ford Robotics building.
Are those lit up wheels?
Yes.
Yes, those are cool. Thank you guys so much. Really appreciate it. Yeah. How I actually had a question, so I'll start us off. I was wondering how your organization handles the knowledge transfer from year to year to make sure that your team can continue to improve even though members graduate.
Yeah, so this is definitely something that we constantly have to improve on. I think recently we have made major improvements on documentation in general. We make just a lot of documents outlining how we do things so that the people taking over can just look over those and kind of build on that knowledge. But I think one thing that really carries us forward is the fact that people, after having a leadership position, they oftentimes stick around. Many of our students go on to grad school, and even then, they still pay attention to the team and make sure they kind of have some sort of oversight for the current leads to make sure things are going properly. And we just have a very strong base of mentors and experienced members that we reach out to whenever we need help. So luckily we have that going for us. Maybe we'll have a decline of that, but at that point, hopefully we have a very strong base of documentation.
Great, it's good to know. I think a lot of project teams can learn from that. So, do you have a question?
I do actually. You might have mentioned this, but how many subsystems are on MRover?
I believe it's 14. It actually could be 15. I think we split up one, so okay. We do occasionally change, yeah. But there's about 15. We also have a business team and executive board, so all in all, a lot of students.
you use all those members.
Yeah.
Nobody's just sitting around, I'm sure. Yeah, do we have any questions from the audience? Feel free to put it in the chat or raise your hand. Otherwise, we'll keep asking questions because we've got more. So what about, let's see. What influences your changes in rover designs from year to year? You mentioned that you have like the in-house testing, which I'm sure is helpful, but not having a competition or feedback, how does that work as far as like the past 2 years and not having the competition?
Yeah, so definitely not having competition, definitely negatively impacts us. Something we do regardless of whether we have a competition is heavy testing at the end of the year, just to validate all the requirements. We try to do testing that resembles the actual competition, so we can see if we met all our goals. I think a big part of this challenge is that everything is so difficult that we always know that we can do better. Even after we built the thing, we instantly know improvements that we can make. When we do have a competition, we do a lot of, we take a lot of notes at the actual competition. We take a lot of footage as well, so we can analyze that the following year. Not only do we try to specifically improve on all these changes that we have in mind, but we also are just willing to kind of try new things and accept different design challenges as well. So, we pride ourselves in the fact that we change up our design a lot every year, just because we have new people, we have new ideas, and we like the challenge.
Great, thanks. There's a couple more questions in the chat, so I'll go ahead and read the first one. From Drew, what do you do with the rover at the end of the year?
Yeah, so this is definitely a question we get a lot. So I think some people say we should like drive it off a cliff or something, or I don't know, do something crazy with it. But there's definitely no reason to destroy it or get rid of it. We have to keep it around. Most usefully for software, because they get to do some testing with it early in the year before the new rover is made. And then eventually there comes a point where we slowly break it down. We start packing it up and storing it in the shelves and things like that. But a lot of the parts we could use in the future in emergencies. So we do have a lot of random rover parts just kind of scattered about.
Nice. Also, the next question, is it possible to access the technical documentation of this rover design? So I'm assuming they're asking like whether it's publicly available after you've made a rover. Yeah. Okay.
We typically don't share any of our any of the actual technical files, such as CAD and any actual code that we write. That's definitely not for the public, just because we do compete at a competition with other schools, and we're one of the more competitive teams out there, and a lot of teams are looking for our help. So we try not to have those things available. But other things like shorter reports and presentations that kind of go over our design, if you wanted to, those are definitely shareable. They're not currently public in any way, but if you email it or something, we can give you some information.
Great.
Yeah, thanks so much for your talk. We're going to go ahead and switch over and get the next presentation set up.
All right.